Now let's talk about some special types of matrices that we encounter often in practice. To begin with, the identity matrix, which will denote I, is a square matrix. It's going to be n by n, and it's a matrix that has ones on the diagonal and zeros everywhere else. So the diagonal elements are all 1, and every other element is 0. And this matrix has the property, which follows very easily from the definition of matrix multiplication, that if we multiply any matrix by the identity, that just equals the original matrix. And by the way, we can multiply it either on the right or on the left, and it will still be that matrix. Important to note, though, that these two identities, this one and this one, are actually different size matrices. They're different identities, right? Because for matrix multiplication to make sense in this case, this A, remember, is an m by n matrix here. This identity has to be n by n, whereas this one has to be m by m. Now, in a lot of cases, we won't actually denote the size of the identity because it's obvious from how we're using it, right? If A is m by n, then if we multiply on the left by the identity, it has to be size m by m. If we really want to, we could write something like a n to denote an n by n identity matrix, but almost always the size of the matrix will be implicit in how we're actually using it. The 0 matrix is another special matrix, which is very common, and we'll just write this as 0. So 0 is kind of a special character in some sense, in that it can represent both just the scalar value 0, but also any matrix, any m by n matrix, which is full of zeros, has nothing but 0 elements, and every element is just 0. Now, this might not seem that useful in practice, right? Because if you say add 0 to a matrix, it will not change that matrix at all. But where it is very useful is in defining block forms for matrices. So for example, if we have a matrix A in m by n and B in p by q, we could form a block diagonal matrix. That's a matrix that has A as its first top left block and B as its bottom right block, and zeros in the two other blocks. We can define C, which is, the sizes of course are going to be m plus p rows and n plus q columns. We can define this as in block form as just A, 0, 0, B. And the size of these 0 matrices, again, are not being written here, but they are whatever size they need to be in order for this definition here to make sense. So in this case, this matrix here would have to have the same number of rows as A, so it has m rows, and the same number of columns as B, so it is m by q. Again, if we want to, we could write something like 0 m by q, sub m by q, to denote that it is that size. But typically, these sizes are implicit in how we use the matrix, much like for the identity. A couple more special cases of vectors and matrices. The number 1 is also special in that it can represent either just the number 1 or a vector in Rn that has nothing but 1 elements. So this vector 1 has n elements that are all 1. This can be very useful, for example, in compactly representing a sum. So if we have a vector A in Rn, and we want to write this term here, we want to write the sum from I equals 1 to n of ai. That's, we want to sum up all the values in ai. We can write that compactly as just the inner product of the 1 vector and a. It's 1 transpose times a. And this one here can sometimes be much easier to write than having a sum every time we want to write something like that. One more special vector is the standard basis vector. This is denoted E sub I. It is a vector in Rn. Again, the size of this vector will usually be implicit in how we're using it. But this vector EI has zeros in all of its elements, except the ith row has the element 1. And this can be useful in many ways, but one example will be to extract entries of a vector or maybe extract columns of a matrix. So for example, if we have a vector x in Rn, then x transpose EI, the inner product of x and EI, well, that would be equal to the sum from I equals 1 to n of xi times EI. I should probably use a different index here, so I'm going to write this as j equals 1 to n, because I'm already using I here. The sum from j equals 1 to n of xj EI sub j. But of course, all these terms are 0 except when j equals I, so this will just equal xi as written above. Another way of thinking of this is EI is the ith row or ith column of the identity matrix. One special type of matrix, which we see a lot in practice, are symmetric matrices. These are square matrices, so it's important that A here is a square matrix. It's an n by n matrix, where we have that A equals the transpose of A. What this means element by element, of course, is that Aij is equal to Aj for all I and j. And these arise very naturally in many settings. For example, for any matrix A, and A here can be any size, and of course because A cannot even be square here, it could be non-square here, we're not assuming A is symmetric at all. But for any A, the matrix A transpose times A is going to be symmetric. And you can easily check that just by this definition of multiplication here, that this property, Aij equals Aji, holds here for this matrix. Another special type of matrix which comes up a lot are diagonal matrices. So a diagonal matrix is defined first using some vector d in Rn. So d is a vector in Rn. A diagonal matrix, which will denote diag d, is going to be an n by n matrix, where all the elements of this matrix are 0, except the diagonal elements, which have the elements of d on the diagonal of this matrix. So for example, one way to use this would be to define, using our definitions from before, is the identity, remember, was a matrix that had 1s on the diagonal. So we could also define that as being equal to diag of 1. This is the all 1s vector. Where diagonal matrices are very useful is in scaling the rows or columns of a matrix A. So for a matrix A here, which is m by n, and a diagonal matrix D, which is n by n, first of all, the product A times D, well, A is m by n, D is n by n, so this product is going to be the same size as A. It's going to be m by n, and it will be equal to A, except that the columns of this matrix are scaled by the corresponding diagonal elements in the matrix D. So multiplying on the right by a diagonal matrix scales the columns of that matrix. And this follows very easily from the definition of matrix multiplication. Remember, the first column of this matrix, one way of writing that was the whole matrix A times the first column, I'll write this as the first column of the matrix D. I'm writing it as capital D here because D1 actually indexes into the vector D, it's the scalar value. So A times the first column of D, well, D1 here has 0 entries except on this first value here. So we're going to take all the other columns of A that are not the first column, and we just throw those away. We don't multiply those by anything. And so what we get for this whole first column here is just the first column of A times D1. This thing is what's equal to that. Similarly, though I won't write it down as explicitly, if we multiply on the left by a diagonal matrix, that is equivalent to scaling the rows of A by the diagonal elements of that matrix. Now, if you can't remember which is which here, if you can't remember if multiplying by diagonal matrix on the right or left scales the columns or rows of A, just think about the size these matrices have to be in order to make sense. Right? So for example, to multiply a matrix A here has m rows and n columns, and D is m by m. Well, D has m different diagonal entries, so it has to be scaling the rows because there are m rows of A. Similarly here, D has n diagonal entries, so it has to be scaling the columns of A.